In this video, we're going to learn about polynomial functions. We start with a motivating example to answer the question, why we care. Have you ever wondered how to make a computer to draw such a picture? Well, it might look a little bit complicated, but it is actually an application of the graph of polynomial functions. If you break the picture down into smaller pieces, then we can actually realize them as the graph of a specific polynomial functions. So for example, this part of the picture is actually a parabola which open down. So actually in this case we use the quadratic function minus I squared plus 6 to draw such a curve. Similarly, for this part, there is also a piece in the graph of a quadratic function, and also for this one. The remaining part of the picture are actually the graph of some cubic functions. This one and this one too. And then after putting all of them together, you get the picture that we already seen in the first line. So this is actually how you can use the graph of polynomial function to draw a picture by computer. So I hope that this is motivated enough for you to study polynomial functions. So let's get started with the definition of a polynomial functions. A polynomial functions is actually an algebraic expression of the following form, where we have a lot of symbol and also addition and equality. So in this expression, actually f is the name of the polynomial function. So we label the function by name so we can easily refer to it later. And x is actually the variable of the functions. The symbol n stands for a non-negative integer, and there's a lot of symbol a, n, minus 1, etc. Until 2, a, 1, and a 0. They are actually a symbol that stand for real numbers, real constant, and we also call them the coefficients of the polynomial functions f. And the rightmost coefficient a0 is actually called the constant coefficient. Now, remark that each of the coefficient a, n, minus 1, etc., they are attached to some power of the variable x. So if we take into account also the power of x, then we have the notion of terms of the polynomial functions. So each expression of the form ak times x power k is called a term of the polynomial functions. Now, very often the leftmost coefficient that we write in the formula of the polynomial functions is actually a non-zero real number. So in this case, we call an the leading coefficient, and n is called the degree of the function, and the whole term an times x power n is called the leading term. Okay. In case an is 0, well, so these notions are actually reserved for the leftmost term that the coefficients start to be non-zero. Okay, we're going to see this in some specific examples so you can easily understand this notion. So these are terminologies for polynomial functions, so you should remember. So you have the name, variable, coefficients, constant one and leading one, terms, and degree of the polynomial. Now let's take a look at some example. We give several polynomial functions and try to identify the corresponding notions like degree, coefficients, or terms. So let's start with fx equal x power 3 plus 2x squared minus 3x plus 4. Then we know that the leftmost terms with non-zero coefficient is x power 3. Then the number n is actually 3, meaning that the degree of the functions is 3. And we have 4 coefficients, 1, 2, minus 3, and 4. And the leftmost coefficient is 1, which is the leading coefficient. And we also have 4 terms, x power 3, 2 times x squared, minus 3 of x, and 4. Okay, but from time to time, actually we might have polynomial function like g of x, where we have 2 times x power 3 plus 0 times x squared plus 2 times x minus 1. And this is also a polynomial function of degree 3 with coefficient 2, 0 to minus 1, leading coefficient 2, and we also have 4 terms, 2 times x power 3, 0, x squared, 2x, and minus 1. But remember that if you multiply 0 by anything, you should get 0 again. And if you add something with 0, well, you have that thing again. So it is redundant to write 0 times x squared in this case. And because of that, actually we can remove that term from the formula of the polynomial functions. But remember that we still write the coefficients of g of x as 2, 0, 2, minus 1. The reason is because if you write only the coefficients of the polynomial functions, then if you remove 0 from these, then actually you cannot keep track of the power of x to which the coefficient is attached. Meaning if now you only write the coefficient like 2, 2, and minus 1, then you cannot tell whether 2 is attached to x power 3 or x power 2, right? So for that reason, even though we can safely remove the terms 0 times x squared from the formula of g of x, when we talk about coefficients of g of x, then you still need to write all the coefficients, including the 0, 1, so that you can keep track of the position of these coefficients in the formula of the polynomial functions. Okay. Whereas similarly here in this case, as I mentioned before, you can give hx where the starting coefficients is actually 0. For like in example, in this case we have a 3, a3 is actually 0, and where in this case again we can safely remove all the coefficients with the 0 on the terms with 0 coefficients, and write h of x like x squared plus 1. So this is a polynomial function of degree 2 with 3 coefficients, 1, 0, 1, meaning that the leftmost is the coefficient attached to x squared, 0, the middle one is attached to x, and the last one, 1, is actually the constant coefficient that is not attached to a real power of x. In this case, we can think about 1 as attached to x power 0, because we have the convention that anything power 0 is actually 1, right? Now, p of x equal 1 is also a polynomial function of degree 0, coefficients 1, leading 1 is also 1, and it's only its sole term is also 1. But if you consider q of x, then equals 0, then because the way we define degree of a polynomial functions, this one doesn't have any degree at all, right? Because its leftmost coefficient is actually 0. So we do not have the leading coefficient in this case either, right? So remember that whenever qx equals 0, then we do not have the notion of degree. Okay, so now let's take a look at some operations including polynomial functions. The first thing that we can define is the sum of two polynomial functions. So if we can write two polynomial functions with the same number of terms, like fx and gx in this case, then you can define the sum of fx and gx by simply taking the coefficient, the sum of the coefficient of the corresponding power of x, like in this formula. Let's take a look at an example where we have the sum of these following polynomials. So you can simply do the computation by pairing coefficient of the same power of x, and then you just need to take the addition of these coefficients, which are actually real numbers, and then actually you do the sum of real numbers, and then you get the answer. But then because you already see that in the formula you have zero coefficient, then you can simplify the formula by removing zero from them from the formula, and the way we write a polynomial function without any zero coefficient is called the standard form of the polynomial function. But from time to time, you might be given two polynomial functions with non-equal number of terms, like in this case. So in order to apply the exact definition of the sum of polynomial functions, you might want to write gx by adding the necessary zero terms. Okay, so in this case, gx and fx now have the same number of terms, and then you can, as before, compute the sum of them by the very definitions, pairing coefficient of the same power of x, and then compute them, and then simplify it to get the standard form of the result. Okay, but what if you don't want to add zero term every time? Then you can actually compute the sum of two polynomial functions by using the vertical formula, meaning that you can write these two polynomial line by lines and align the same power of x into the same column, and then after that you can do the sum column-wise, meaning that for each column you take the sum of the corresponding coefficients, and then you get the answer. Now, it can be easily seen that we can obviously take the sum of a finite number of polynomial functions. Like in this case, if we have three polynomial functions, then we can do this, do the sum of these three polynomial functions either horizontally by regrouping coefficient of the same power of x, and then compute the result as before, simplify to get the standard form, or you can use the vertical formula, write all of these line by line and put this, the same power of x on the same column, and then you can do the sum vertically as before. Now, after the sum of polynomial functions, the natural thing to think about is try to define the product of polynomial functions. So we start with some easiest case. Given a polynomial function fx as shown in the picture, the first thing that we want to take the product of fx with is a polynomial functions of the very simple form g of x equal to b times x power m. So in this case, we can define this product of fx and gx by simply multiply each coefficient of fx with b, and we shift the power of x in fx by m unit. Okay, and then if you have gx of a very complicated form, then you can define the product of fx and gx by first taking the product of fx with each term of g of x, and then After that, you have a bunch of new polynomials. You just need to take the sum of all of them. Then you get the definition for the product of fx and gx. So in order to understand this complicated and a little bit long formula for product of polynomial functions, we can look at an example to understand what is the meaning of this. So for example, here we have fx is a cubic function and gx is a quadratic function. Then if you want to compute the product of fx and gx, then actually first you can break it down into two smaller pieces where we multiply fx with the leading term x squared, and later we multiply fx with the constant term of g of x, meaning fx multiplied by -1, and then you compute the corresponding product. So the first thing you compute is the product of fx with x squared, meaning that you multiply every coefficient of fx by 1, and then after that you shift the power of h power of x by 2 units. So similarly for the multiplication with -1, and then after that you have the sum of two polynomial functions you can easily compute, and the answer now is actually a polynomial function of degree 5. And you can also write the whole procedure in vertically, right? So now if you want to take the product of fx and g of x, in this case, you can write them line by line and then try to compute the product of each term of the second one with the first one from right to left. So for example, first we take the product of -1, the constant coefficient of g of x, with f of x, and you write the result here by line. Secondly, you take the product of fx with x, maybe at this one, and then the last one you take the product of fx and x power 3, and you get this line. And you have to arrange this line column by column, where you put all the same power of x into one column, and then after that you can take the sum as usual. Okay, this gives us the result. Now we come to define the equality of polynomial functions. Here we adopt the way to define two equal numbers. So remember that if you want to define two equal numbers, you can actually first define the equation, the equality between a number and 0. Then after that, you say that a number m is equal to a number n if the difference m minus m is actually 0, right? So first of all, you say that a polynomial function fx is a 0 polynomial function if all of the coefficients of f of x are actually 0. And after that, for a given polynomial function fx, we denote fx times -1 by minus fx, meaning that you just need to negate every coefficient of f of x, right? And when you have the notion for minus fx, then actually you can define the difference between fx and gx by simply putting fx minus gx, the result fx plus minus g of x. Okay, and then after that you can define fx and gx are equal if and only if the difference fx minus gx is 0. Okay, so let's take a look at an example. So you have fx is a quadratic functions, and gx is actually given as the product of two linear functions. So in order to compare fx and gx, first of all, you just need to compute g of x using the formula to compute product of polynomials, and you get the answer that gx is also x squared minus 2x plus 1. From the definition, now you need to compute g minus gx, right? Then after that, you take fx minus gx and you get 0, meaning that fx is equal to gx. But another way which is might be a little bit easy to realize that fx is equal to gx is that we can compare, first of all, the degree of fx and gx. If they are of the same degree, then after that you compare the coefficient of the same pairwise. If they still are all the same, then fx is actually equal to gx. Then that is actually the way we can compare two polynomial functions and tell whether they are the same or not. Okay, so we already talked about the sum of polynomial functions and product of polynomial functions. So now what about division of polynomial functions? So as for number, we also have Euclidean division for polynomial functions. So here given two polynomial functions fx and gx. If we know that gx is not the zero polynomial functions, then we can find the unique polynomial functions qx and rx such that first fx is equal to gx times qx plus rx, and secondly rx is equal to 0 where we have no definition of degree, or we know that the degree of rx when defined is strictly less than the degree of qx. So this is actually reminiscent of the Euclidean division of polynomial functions, and for that reason we call qx the quotient, rx the remainder, fx the dividend, and gx the divisor of the division of fx by gx. Okay, so the rule is the dividend is actually the product of divisor and quotient plus the remainder. Now take a look at an example to see how it works. So here you have a polynomial function of degree 4 on the left and another one of degree 2 on the right. If you want to take so the left one is actually fx in this case, and the second, the right one plays the role of gx. Okay, so now if you want to define fx by gx, so you just need to take the higher terms of fx and divide it by the highest term of gx, right? And you get the answer, which is 5y squared. And after that, you multiply gx by the resulting one, and then actually you get this polynomial functions. Then you take the difference between these vertically, then you get a polynomial function of degree 3, which is already 1 degree less than the original dividend. Okay. Now you do the same trick again. You take the highest terms here, divided by this one, and then you get the second term in the quotient. Okay, this should be the quotient in the end. Okay, and then you take the multiplication of this one and this one again, put it down here, and taking the difference of these polynomial function, you do the same trick again, and you get the third term of the quotient, and then actually in the end you get this one. So remember that this one is already a degree less than this, so this is actually the remainder, and this is the quotient of the division of fx by gx. Okay, so you still have the rule dividend is equal to the product of divisor and quotient plus the remainder. Okay, let's take a look at another one. So in this case, you keep fx, but you modify gx a little bit by adding -1 to the formula, and you do the same computation all over again. And then now when you arrive at the end, you see that the remainder in this case is 0. So in this case, actually the remainder does not contribute anything to the dividend. So the dividend is actually the product of divisor and the quotient. Okay, so in this case, actually each of these polynomial is called a factor of the dividend. Okay. And each of the factor, so you say that the dividend is divisible by each of these factor. Okay, so you have the notion of a factor of polynomials, and you also have the notion of factoring a polynomial fx. So factoring a polynomial meaning that you try to write or express f at the product of a number of polynomial functions of degree strictly less than the degree of fx itself. Okay. So for example, x power 4 minus 1 can be written as the product of three factors. The first one is x squared plus 1, the second one is x minus 1, and the last one is x plus 1. They are all polynomial of degree strictly less than 4. Now we talk about very important notions, including polynomial functions. That is, we are going to talk about zero of polynomial functions. We say that a real number alpha is a zero of a polynomial function f if whenever we evaluate f at alpha, we get 0. One important fact about zero of a polynomial function is that if alpha is 0 of f of x, then x minus alpha is actually a factor of fx. And this can be easily seen from the Euclidean division of fx by x minus alpha. So let's take a look at the argument. If we call qx and rx the quotient and the remainder in the division of fx by x minus alpha, then actually we know that because the degree of x minus alpha is 1, then either rx equals 0 or the degree of rx is 0, meaning that rx should be a real number, a might be 0 or not. So when a is 0, we know we do not have the degree of a, but when a is different from 0, then the degree of a is actually 0, right? So it's followed from the Euclidean division of fx by x minus alpha that, first of all, when we evaluate f of alpha, we get that f of alpha is actually the product of alpha minus itself times cube alpha plus a. But alpha minus alpha is actually 0, so what we get here is actually a, the remainder. On the other hand, as alpha is 0 of f of x, then f of alpha is 0. So we get 0 is a. So this justifies the fact that if you want to, if you have alpha as a 0 of f of x, then x minus alpha is actually a factor of f of x. Okay. Now we can actually bound the number of zeros that a polynomial function should have. So the statement is that if fx is not a constant polynomial function, then f has at most n real zeros. Indeed, if f of x is equal to ax plus b, meaning that we test the easier case of polynomial function, the linear one of degree 1, where a is different from 0, then it can be easily seen that the only 0 of fx is minus b over a. Okay, so in this case, the assertion holds. Now, we can actually proceed by induction on the degree of f. So, suppose that we already have the assertion for all polynomial functions of degree less than or equal to a given number k. Then, let f of x be a polynomial function of degree k plus 1. If f of x has no 0, then the assertion obviously holds, right? But when fx have at least one zero, let we call the zero alpha, then because we can actually factor fx as x minus alpha times g of x for some polynomial gx, then we know that from this formula, gx is actually a degree strictly less than f. And in this case, the degree of f of g of x is actually k. Then by the induction hypothesis, we know that g of x has at most k real zeros. And because the zeros of f of x is actually alpha and all the zero of g of x, then it follows that f of x has at most k plus 1 real zeros. So by induction, well, we can easily verify the statement that a non-constant polynomial function of degree n has at most n real zeros. Okay. Now we talk about multiplicity of zero, meaning that from time to time we might have more than one factor of x minus alpha in a polynomial function of x. So we call m the multiplicity of alpha if x minus alpha power m is a factor of fx, but x minus alpha power m plus 1 is not. Okay. So for example, in this function fx, then we can see that x have actually 3 0, 0, 2, and 1 over 2. 0 is actually a multiplicity 1. 2 is actually a 0 of multiplicity 1, right? 0 is a 0 of multiplicity 2, and 1 over 2 is a 0 of multiplicity 4. Now we talk about the graph of polynomial functions, which is something quite important, as we already seen in the introduction of polynomial functions, because actually we can use them to draw some kind of nice picture using computer, right? So let's take a look at the graph of the following function shown in the slide. So before we try to draw the graph of the functions, let's try to identify some notion, some corresponding notion of these polynomial functions. So first, we can see that the degree of the functions is 10 because here you have the product of 4 polynomial functions. This one you have degree 2, this one of degree 2, this of degree 5, this one of degree 1. So you have 1 plus 5 plus 2 plus 2, which is equal to 10, right? And the leading coefficient is a multiplication of this one and the leading one of each of these, meaning that the leading coefficient is 1 over 1,600, which is a positive coefficient. All right. And the next one, you can actually identify the constant coefficient. That is the product of this one and the constant one of each of these factors. And we can easily compute it and get the answer 18 over 25. So the meaning of constant coefficient in the graph of the polynomial function is that it's going to give us the y-intercept, because when we evaluate this one as x equals 0, then actually we can get the constant coefficient. So the y-intercept or the intersection of the graph with the y-axis is actually the point with coordinates 0, 18 over 25. Okay. So now we can also identify all the zeros and multiplicity of them of the polynomial functions. So remember that the zero of a polynomial functions, when we evaluate f at each 0, we get 0. So this will actually give us all the x-intercept of the graph of the functions. So here we have actually 4 x-intercept, meaning we have 4 intersections between the graph and the x-axis. Minus 3, 0, minus 1, 0, 2, 0, and 4, 0. Okay. So now let's take a look at the variation of fx when x is far, far away from where the zeros lives. These are called end behavior of the polynomial functions. So in this case, outside 3 minus 0 and 4 0, right? Then the value of fx tend to plus infinity on the both sides. So this is called the end behavior of these polynomial functions. So remember how the value of fx vary when x tend to minus infinity or to plus infinity is called the end behavior of the polynomial functions. This one depends on first the degree of the polynomial function and later on the leading coefficient. In a couple of minutes, we're going to see this in more details. Okay, so in this example, let us just introduce the notation and the terminology for this kind of phenomenon. Okay. So now, inside the realm of zeros of the polynomial, first look at the leftmost 0, minus 3. So, of course, from minus 3, 0 to minus 1, 0, the graph of the polynomial function should stay somewhere in between. And in this case, actually, where for fx from minus infinity to minus 3, then the graph of the function decrease rapidly to this point, but then after that it rebounds and increase up to this point, and then it decreases again. So we can actually explain this phenomenon here. The fact that through this point the graph of the function rebounds, meaning that the graph will only touch the x-axis but do not cross. This is because the multiplicity of minus 3 is actually 2, an even number. Okay, so for that reason, when the multiplicity of 0 is even, then the graph will touch the x-axis at the corresponding x-intercept. Okay, and then because it's rebound, and then for its one to rejoin the next x-intercept, then the graph should somewhere start to decrease. Okay, and it decrease until it meets this point. So it gives us 2 specific points. Through them, the graph of the function actually changes direction. So first is the x-intercept minus 3, 0, to which f changes from decreasing to increasing, and the yellow one point here, to which the graph turns from decreasing to increasing. All right. So now take a look at the next x-intercept 2, 0. Okay. Then from minus 1, 0 to 2, 0, there also be a part of the graph of this function. So now from the explanation for this one, you can already guess what is the shape of this part of the graph. Well, take a look at the multiplicity of minus 1. This is 2, an even number. So from this point, the graph will also touch the x-axis, meaning that it's going to rebound and pass through this one, and somewhere from here it will start to decrease to rejoin the x-axis to 0. Okay, so here we have another turning point And the same here. Now 2 have multiplicity 5, which is odd, meaning that here the graph will no longer rebound. It will actually cross the x-axis and rejoin for 0 here. Okay, and it will give us another turning point down here, right? So from this we already have new terminology for the graph of polynomial functions, the end behavior and the turning points, right? And we also understand what is the meaning of multiplicity, even multiplicity, meaning that touch the x-axis, and odd multiplicity, meaning that the graph will cross the x-axis. Okay. So to review, a polynomial function of degree n has at most n minus 1 turning point. That is a very important fact about polynomial functions. When we learn about derivative of a polynomial function, we're going to see why this fact is true. But from here, we can just admit this fact. A polynomial function of degree n has at most n minus 1 turning points. Keep in mind about that. The next thing is the behavior of the graph at a turning point with respect to the multiplicity of 0. Now, an x-intercept is actually a turning point of the graph if the multiplicity of the corresponding 0 is even. Okay, and well, for a 0, when we talk about multiplicity, we can divide it into two cases, even multiplicity and odd multiplicity. So we already know that when the multiplicity is even, then the graph touches the x-axis, meaning that the corresponding x-intercept is actually a turning point. And for odd multiplicity, the graph will actually crosses the x-axis. Now we will be more precise about the behavior, the end behavior of polynomial functions. We already mentioned before that the end behavior of polynomial function depend on the degree and the leading coefficient. Now we divided them into several cases. So first, if the degree is odd and the leading coefficient is positive, then so first, if the degree is odd, then we know that the end behavior where x tend to infinity and the end behavior where x tend to minus infinity, they head into different direction. So whenever the degree is odd, we know that the end behavior goes into different direction. And here in this case, if now you consider the leading coefficient, if that is positive, then when x go to plus infinity, then fx also go into to plus infinity, and of course fx must go to the opposite direction when x tend to minus infinity. And when the leading coefficient is negative, then when x go to minus infinity, actually fx will go to plus infinity, and vice versa. If x go to plus infinity, then f of x will go to minus infinity. So remember that first of all, if the degree is odd, then the end behavior should be on different directions, and it depends on the positivity or negativity of the coefficient, the leading coefficient, that we can determine actually where the value of fx will go, depending on where x go to minus infinity or x go to plus infinity. Now, if the degree is even, then we know that the end behavior should behave the same way, meaning that whenever x go to minus infinity or plus infinity, fx still go to the same direction. And also, so if we want to know whether it's go up or it go down, then we look at the leading coefficient. For in this case, if the leading coefficient is positive, then the end behavior will actually go up. And if the leading coefficient is negative, then actually the graph will go down, the end behavior will go down in both directions. Whenever I go to minus infinity or I go to plus infinity. Okay. So by now, you should be able to recognize which of the following graph correspond to which of the following polynomial functions. Okay, I could leave this as a keys for you so that you know whether you already understand the meaning of various notion and notation about polynomial functions. So I hope you enjoyed the video.